Now, one of the very nice thing about alternating series is that this is a series where we can easily estimate what the limit is going to be of that series. We can try to figure out what number should this infinite sum be converging to. So what we're going to do is we are going to take advantage of that jumping idea that I had in my demonstration. So the idea is that my limit should be wherever all of the numbers cluster on the real number line. So again, I know that my limit is going to be here. But notice that the limit is not very far away from the individual partial sums, right? Maybe this is S sub 6 right here. How close is that limit to S sub 6? I can figure that out based on the very next term that I am adding to the partial sum. So the important thing about the alternating series test is that alternating series converge as long as the step size is shrinking and going to 0. If I stop at some amount, how far away am I? That only depends on the next jump I would have to do. So the size of the error is going to be smaller than the very next step, b sub n plus 1. So put in a formal perspective, here I've got an alternating series. We're saying that this alternating series converges to a value of s. And each step we are adding on the number -1 to the power n minus 1 times b sub n. So we know that this converges, and we want to ask how far away from the actual value of the limit are we if we stop at step n. So as usual, s sub n is my nth partial sum. That's what I get from adding up the first n numbers. And we'll call that capital R sub n, R for remainder. Well, the absolute value of this remainder, or the absolute value of the truncation error, if you prefer, is going to be less than or equal to the very next step I'd have to take in the alternating series. So what is the size of the next jump? So let us calculate what is the sum of the series starting at n equals 0, going up to infinity, where I'm taking -1 to the power n and dividing by n factorial. So just as a reminder, the factorial function is just the product of all the integers starting at 1 and going up to n. And n and 0 factorial is just defined to be 1. So this is an alternating series, and it does converge according to the alternating series test, since each of the fractions on my list in absolute value is going to be less than the absolute value of the fraction that came before it. Again, I'm just making these denominators larger and larger. In the limit, as n goes to infinity, these fractions are going to go to 0. That's my alternating series test. Now let's actually find a value for this thing. I know that my first couple of terms here are +1 and then -1, +1/2, -1/6, +1/24, and so on. How far do I have to go out to have the value of the limit correct to 3 decimal places? Well, if I stop at n equals 6, I will be off by the 7th number in my list. So stopping at 1 over 720 means that my error will be less than 1 over 5040. But 1 over 5040 is, less than 0.0002. So if I stop at S6, this is telling me that my error will be in the 10,000s place, which tells me that the first 3 digits are correct. So I can calculate the sum of the first 6, stopping at S sub 6, and I get 0.368 and change. This will be off by some small amount, so I can't really trust any of my decimals past the thousandths place. But I know that that limit is going to start off 0.368. So the first 3 decimal places of this series are 0.368. So this gives us a way to estimate the value of an alternating series by adding up just the first couple of terms. Now, one thing to be careful about here is that this rule only works on the alternating series. It's specifically because of this leapfrogging behavior, where I am always turning around and going back the other direction, and each successive jump is less than before. That is what makes this estimation work. And so we really did need the plus and minus signs on the series for this to work.